I wanted you to see another example. In particular, we're taking an approach that in my opinion is easier, but it's not in the book, and so I want to make sure you saw another example at least of what we're going to do that doesn't use the triangle equality repeatedly. So we're going to look at this integral, negative infinity to infinity, quantity x plus 2 dx over the quantity x cubed plus 8I. For the exam 3, we're going to consider problems such as this one, which can be done using the u sub r upper semicircle as the auxiliary curve. Using this u sub r, we notice that we get the sum of these two integrals, negative r to r, x plus 2 over x cubed plus 8I dx, plus the integral over u sub r, t plus 2 dt over t cubed plus 8I quantity, is equal to the integral over a closed curve, c sub r, quantity t plus 2 dt, t plus 2 times dt over t cubed plus 8I. Also notice that t cubed plus 8I is equal to 0 if t cubed is equal to 8I cubed. And here I'm using the fact that I cubed is negative I, so t cubed equals negative 8I is the same as t cubed equals 8I cubed. And because of that, the poles we can get by taking the cube roots of 8I cubed, and there are going to be 3 of them. The first one's 2e to the I pi over 6, then 2e to the I pi over 6 plus 2 pi over 3, and then 2 to the ei pi plus 4 pi over 3. And that simplifies to 2i, negative square root of 3 minus I, and the square root of 3 minus I. When we draw the zero pole diagram, however, we notice that only 2i is inside the closed curve c sub r. And I also drew the 0 at negative 2, but it doesn't play a role here. All we're looking at right now are where the poles are. So that means we need to evaluate the integral c sub r at the pole at 2i. So I'm going to use the residue theorem. We have one pole, and we need the residue at the 2i pole of t plus 2 over t cubed plus 8i. It's a simple pole, so we can evaluate it by taking a limit of, as t goes to 2i, of t minus 2i times that integrand, t plus 2 over t cubed plus 8i. And that's going to give me 2 pi I times the limit, as t goes to 2i over t minus 2i over t cubed plus 2 plus 8i. So t minus 2i quantity over t cubed plus 8i. And notice both of those are equal to 0 at 2i. The other part, the t plus 2 that's in the numerator, we put it in a separate limit because we can just substitute to evaluate that. And in general, you'll just put everything you can substitute in one limit and whatever you need to use the L'Hopital's rule in another limit. Now that's 2 pi I. The limit as t goes to 2i, 1 over 3t squared. We substituted and got 2i plus 2. And of course the first one we use L'Hopital's rule. Derivative of t minus 2i is 1. Derivative of t cubed plus 8i is 3t squared. Now we can substitute in that remaining limit, and that'll give us a 2i squared in the denominator times that 3. So we got 2 pi I times 1 over 3 times 2i squared, which will be negative 4, and then times the 2i plus 2. And when you do all the algebra and work all that out, you get pi times the quantity 1/3 minus I over 3. And what we're hoping is that's actually the answer. If it is going to be the answer, we have to answer the question, does the auxiliary integral vanish? So let's compute the limit as r goes to infinity of that integral. But here's where this theorem that we proved in class comes in. Everything else that we've done is just like in the book, but our theorem says that we can look at the limit as r goes to infinity of the absolute value of r, f of rei theta. In this case, that would be the limit as r goes to infinity of absolute value of the quantity r times r e to the I theta plus 2 over r cubed e to the 3I theta plus 8I, substituting the re I theta in for the t. And that limit is going to give us an r squared plus ei theta plus 2r on top and an r cubed e to 3I theta plus 8I on the bottom. R cubed is the dominant term, so we divide the numerator and the denominator by the dominant term. And this is very much like something you do in high school, where you compute a limit by dividing by the dominant term, and that's going to give us an ei theta over r and a 2 over r squared and an e to the 3I theta and an 8I over r cubed. And when you do that, you get 0 plus 0 over e to the 3I theta plus 0, but regardless of what theta is, that quantity is 0. So therefore, the limit as r goes to infinity of the integral over u sub r t plus 2 dt over t cubed plus 8I is equal to 0. And that allows us to put it all together. So remember, we said we had this integral from negative r to r plus this integral over u sub r equal this integral over c sub r, the closed curve. And now we're going to take the limit as r goes to infinity of each of these three. And so we got the limit as r goes to infinity of the negative r to r, x plus 2 quantity times dx over the quantity x cubed plus 8I, plus the limit as r goes to infinity of that integral over u sub r, and that has to be equal to the limit as r goes to infinity over c sub r, that closed curve. But our answer for c sub r is independent of r, because no matter what r is, we get pi times the third minus I over 3. And therefore, we get the integral we're trying to evaluate plus the limit as r goes to infinity of the integral over u sub r, t plus 2 dt over t cubed plus 8I equals pi times the third minus I over 3. But on the last slide, we showed that that remaining limit is approaching 0, and so therefore we have the problem we were wanting to solve equal to the answer we got from the residue theorem. In other words, negative infinity to infinity, quantity x plus 2 dx over the quantity x cubed plus 8I equals the answer pi times the quantity 1/3 minus I over 3.